Hi, welcome to episode 3 of Inspiration Basic Programming with Tim. This is probably the 4th time I've tried recording this. Ran into a few different problems here and there. From trying to write this a certain way to my computer crashing. But we are going to create a new algorithm, one that I haven't been used to creating, called an Armstrong Sequence generator. And what we're going to do is create these numbers, or try to find these numbers that that are equal to the sum of the cube of each of their digits. So, for example, the number 371 is equal to the cube of 3 and the cube of 7 and the cube of 1. And other numbers that I found online that are examples are like 0, 1, 153, 370, and 407. So if we create this generator and find those numbers, then we will see that we successfully kind of created this generator. So let's start with a number kind of counter. I found that there's different ways I was trying to do this, and one of them was kind of generating numbers from digits, but I think I'm just going to start with a number and then break it down into its digits. So I'm going to say while this number is less than, we'll go up to 1 million. And then, just for debugging purposes, at the start, let's go ahead and just print out the number so we can see which ones are being tested. And then let's go ahead and break it down. So, to break it down into its digits, we're going to have to make a loop. And one thing I'm going to do is I'm going to copy the number because I'm going to break the number down. So we're going to go ahead and we'll just call it the copy, because the copy is going to get mutilated. And we're going to say while the copy hold on. We're going to say while the copy is greater than 0. So while there's still more to the copy, we're going to chop it up a little bit more, but we're going to when we chop it up, we're going to do it by factors of 10 here. So we're going to start off, and we're going to have this this part of it, and we're going to take this remainder. So let's call it R for remainder. And we're gonna say that's copy. We're gonna use the remainder operator. We're gonna say copy remainder I kind of want to say 10, although we might have to put a multiplier variable there and just multiply that by 10 each time. But what I could do is I could divide copy by 10 each time. That's another thing I could do. And that might that might not be the right choice because I don't know how large the magnitude is. So I'm probably going to make a multiplier. So let's go ahead and make this multiplier, and we're going to set it to 1 because that's kind of the base for multiplication there. And well, let's see here. We do want to get the smallest part of copy, so you know what? We might have to just go ahead and start this at 10 because that's when we first are using it. And then we're going to multiply it by 10. So I'm going to say multiplier equals multiplier times 10. So let's say we have the number like 35, right? So the first number we're going to get is 5, and then we want 30 because we're going to have this multiplier, and we're going to take the remainder of that in 10, okay, and then that leaves us with 5. But we want to subtract 5 from the copy so that the next time we go around doing this, we get 30, and that's it. We don't get any extra numbers. So we're going to go ahead and say copy equals the subtraction of copy, and I don't want to put in 5. That's just for our one example. We're subtracting out r because that's what the remainder was. So here we go. We have copy is greater than 0. That means there's still more to it. So we still need to kind of make it, still need to kind of get a bigger chunk to it. There's still a level up. And then here we get that the smallest chunk, the next one. And then we multiply it to prepare for the next one, and we subtract this to prepare for the next, kind of the next one. So that seems to be a good way. So one thing that I want to try to do is I want to print false here. That's going to mark. So we're going to see our number, and then we're going to see how the number breaks apart. And let's see what that does. That does not work yet because I'm not incrementing number. So let's go ahead and increment number. So number equals the sum of number and 1. And we got to put that on the outermost loop. So let's go ahead and do that. Okay. So it didn't seem to keep printing after we reached 10. Kind of got stuck somewhere. That's not good. We should change this to multiplier though. That might have been the problem. So let's go ahead and try that. Oh, there we go. Okay. So let's go ahead and, I don't know if this is working properly, so let's go ahead and print the chunks. I want to print to see what R is. So I'm going to print R right here, and we're going to see if that works. Let's go ahead and run it. We're going to stop it. So here we go. 47 is made up of 7, then 40. Starting from smallest and getting the largest. So yep, that seems to work so far. Okay. So next, and by the way, it looked like it was running slowly, but it's running slowly here because we're using the output. The output is really slow compared to the computation. The computation is probably at least 1,000 times faster. I don't know how much faster it actually is. Print R. multiplier. Okay, so we need to cube it now and add it to this kind of this sum that we're going to get. So let's go ahead and copy equals number. Let's go ahead and we'll start something called a cube sum. And I'm going to use something called Camel Casing. That's kind of making a variable without any spaces or underscores, but still having multiple words, and use the capitalization to kind of mark the different words that composes the variable name. So cube sum, that's like 2 words, and use this capital S to say, hey, this sum is a separate word than this word cube, so it's easier to read. So we're going to start the cube sum with 0. And then we're going to add whatever r is, we're going to add cube sum to it. So we're going to say cube sum equals the sum of cube sum and r. And that way we can see, that way we kind of have this completed kind of thing, and then we're going to print the cube sum just to kind of see what it gives us. So let's go ahead and do that. Okay, so we got 28, 820, and then it says 28 again. And that does not seem right because, well, it is correct. Program is always correct. It always does what I tell it to do, but I did not implement this correctly because I actually don't want this to add r. I want this to add the cube. So I want it to add the multiplication of r and the multiplication of r and r. So let's go ahead and let's see what that does. Ooh, those are pretty big numbers. Those are pretty big numbers, and I don't like how r is getting bigger. That's not good. I'm not supposed to get 40 or 7 or something like that. Actually, earlier when I was talking about using the multiplier would probably be the better way to go. No, I think I was wrong. Because I don't need to keep track of which digit it is. It actually doesn't matter, to be honest, because I'm supposed to add the cube of each individual digit. I'm not supposed to add the cube. I'm not supposed to take 3 cubed plus 70 cubed, or 300 cubed plus 70 cubed plus 1 cubed. No, it's 3 cubed plus 7 cubed plus 1 cubed equals 371. So yes, let's just get rid of this whole multiplier thing altogether. And instead of subtracting this, what we're going to do is we're going to do copy equals copy divided by 10. That's what we're going to do. Okay. And then this whole multiplier thing, we'll get rid of that. And then this thing, r equals copy. And no, this should be a 10. Okay, so that means whatever our lowest amount is, we're just getting rid of that information down here anyway. So even if we have 35, well, the 5's going to be gone, so now we just have a 3. So yeah, that works. I think. Well, I can't say it for sure if it works until I run it. Let's see if that worked. 26, 224. Interesting. So is this working? Well, let's scroll to the top. It looks like it works for 1. It doesn't look like it printed out for 0. I'm not sure why. Oh, because 0 has 0. Because 0 doesn't even enter this kind of loop thing. So, so what we're going to do is we're going to go ahead and just erase these. Print false. Print number. Yep, let's erase those. And then print R, let's erase that. And we're going to change this. We're going to say if cube sum equals number. Okay, then it doesn't matter which one we print. We can print one or the other. They're both the same anyway, so we can just print the number. Wow, that's one. Look at that. That's the size of your iPhone. Let's see if that works. It worked. Look at that. What do you know? What do you know? Those are the Armstrong numbers I was looking for. And it is still searching too, isn't it? It is still computing. And it hasn't found any more. What do you know? It is still searching. You know what? Tell you what. This is going to be the end of the episode. When I do my next episode, I will run this in the background. See how it's running? I will let this run in the background, and we will see if any more numbers show up. How's that? If none show up, well, if none show up, that might not be very exciting, but I'll let this run for a while, even when I'm not programming. We'll see. We'll see. So, but there we go. We did it. This is it. This is correct. These are the correct numbers. Those are Armstrong numbers right there. So, there you go. And it's only one iPhone size height worth of code. 1 page worth of code right there on your phone. Armstrong number generator. And guess what? We can use full variable names. Who can say that about their programming language? Who can say that their programming language lets you use full variable names and you program it on your phone? So, it's been nice. Thank you for watching episode 3 of Programming Inspiration Basic with Tim. I hope to see you again in the next episode. Goodbye. Hi, it's Tim again, and we're still on episode 3. Actually, I am back to talk about a mistake that I just made. I was misled by a website that claimed that an Armstrong number was a number that is the sum of the cube of the digits. That is actually not entirely accurate. So what is an Armstrong number? It is actually a number that is equal to the sum of the exponent of each of the digits to the power of however many digits there are total in that number. So these right here, these are actually Armstrong numbers. These truly are. But there's a few missing. Actually, 2, 3, 4, 5, 6, 7, 8, and 9 are all Armstrong numbers. They're also called narcissistic numbers. That's another name for Armstrong numbers. And the number 1,634 should actually be included, but I believe it is getting skipped because we're not computing these correctly. So, I'm going to go in through here, and let's try to correct this. So we're not gonna use cube sum anymore. Okay. We might as well just call this power sum. Because that is what it should be. And we need to alter a few things, so this is not going to fit on a single page, but it's still going to be pretty compact. We're going to take this power sum, and we're going to find out just how many times we need to multiply this number. Just how many times we need to multiply this number's digits by themselves. And in order to do that, we need to actually compute here what the number sort of size is, if you will, its magnitude. So we're gonna say while let's see here. Copy. We could say there's multiple ways we could do this. I guess it doesn't really matter how exactly we do it. But let's just go ahead and do it this way. So we'll just say while copy is greater than 0, and we're going to copy is divided by 10. So let's go ahead and just divide copy by 10. And but we're also going to have another number, and it is going to be our power that we're going to use. And I think we're going to start it off at 0, and then for each of these we increment it by 1. So we're going to say power equals power plus 1. So now we have kind of a magnitude measurement of our number, and then we want to set copy to number again, so we're just going to go ahead and say copy equals number so that we can mess with it again. Now power sum is going to equal 0 at the start because it's going to be a sum. We're going to come down here, we're going to get the remainder, and we're going to say power sum equals the sum power sum plus, and then we're going to make a new variable, and it is going to be, it's not going to be the power, but it's going to be, what is it called after you take the power? Maybe, because power, if that's the superscript, what is the number called after you take the power? I shouldn't actually know this, but I'm going to call it the product, because we are going to be multiplying anyway, so technically, I mean, it is kind of going to be a product one way or another. So we'll just call it the product. But I need to compute this product. So how do we compute this product? Well, we're going to say, well, I'm going to use I actually, is less than power. And let's put an I in here. So we got to say I equals 0. Okay, so we're going to have this loop. So up here, I added this loop. That's going to tell us kind of the magnitude, how many digits our number has. And then down here, what I'm going to do is I'm going to have to add a loop that kind of takes it to the power, because we don't have a power kind of command in here. I can't say like what's 5 to the 4th power. I have to multiply 5 4 times. If I don't know how many times it is, I'm gonna have to do a loop that does it however many times we need, that's what power is. So I'm gonna say I equals 0 while I is less than power. Okay, and we're gonna increment it. I equals I plus 1. Because I know I'm going to need that statement in there. But what are we going to do? We're going to add to the sum, or we're going to add to the product. No, multiply the product. So product. So I'm going to say product. I'm going to say product equals R to begin with. And then while I is less than power, product equals product times R. So product is kind of just going to multiply itself by R a few times, and then we're going to get some sort of something to add to power sum. Let's see what that does. Cube sum does not exist. Where am I using cube sum? If cube sum equals no. If power sum equals, let's try that again, 0, 1, it is still computing. Oh, that does not look correct. 4150 and 4151. That is not correct. I believe. Let's try something. Let's go ahead and make I equal to 1. Because I think it's multiplying 1 too many in there. Let's try that. Oh, that looks correct. Oh, and that is correct. Oh, that is correct. Those are correct numbers. I'm able to check them right now because I actually have a list from Wolfram, and 1634 and 8208 and 9474. Those are all numbers. It might be a while before the next one shows up. Might be a few, because the next one is 54,748. There we go. Okay, so those are the narcissistic numbers. Those are the forget what you call it. Let's see, how long will it be till the next one shows up? It should only take about 3 times as long as the previous one. But it'll still be computing, so we don't have to, take forever. I mean, it will keep going until it reaches 1,000,000. There is an issue that I found out that I do want to fix with my app. Not enough people really have used it enough to report this yet, but I do realize, and I kind of feel a little concerned about this, that if the output finishes, if your program kind of finishes computing, then you no longer can go ahead and see the screen. You can't come back here. It kind of just finishes and you don't get to see it. And I don't like that. It kind of forces you to have to put like an infinite loop here at the end or something, and that's silly. So maybe I should make it so that you do have to press this X. You do have to stop the program or something at some point, because otherwise there's no way to see this once it's done. So I might fix that kind of problem with my app in the future. We'll see how that, if it bugs, maybe if it bugs enough people and I haven't fixed it yet. Just go ahead and report it if you find it to be a problem, and I might put some time into it. So there we go. There's our correct Armstrong generator, using the correct definition of Armstrong numbers, and all these numbers so far are correct, and it hasn't missed one. So there you go. That is the real end of episode 3. I hope you enjoyed it, and goodbye.